Today we're doing some more Calculus 2 practice problems, focusing on finding volumes of solids formed by revolution using the washer method. So what is the washer method? We know the disk method, right? So think of this as the subtraction of two disk methods. We could think of this shape right here as just an outer cylinder with this volume, and we're going to subtract that inner cylinder with little radius r, right? So this volume of this cylinder can now be found using geometry. It's pi h and then r squared minus little r squared, right? And we're going to do the same thing, but what if one of those radii are variable? Then we have to integrate, right? So what we could do is we could take a slice and revolve it, and notice now instead of being a disk, it is a washer, hence the name, the washer method. So we can find the volume of that little slice, which is the same as that of the cylinder, right? Except it has a height delta y. And we can take the limit as n approaches infinity of the sum of all those little delta volume disks or washers. And that just becomes an integral from 0 to h of dv. dv is just this pi r squared minus little r squared dy, right? And we're still going from 0 to h. So let's look at an example. This asks us to find the volume of the solid formed by revolving the region about the x-axis for both of these equations. So let's look at this one. When we revolve it around the x-axis, what are the steps to making the solid? Well, you reflect it over the axis you're revolving around, right? And then you connect the identical points. So this one comes to here, and that one goes back. This one comes to here, and that one goes back. And then it kind of makes like a, does that make it better? It's almost like a big sphere with a cylinder taken out of it, kind of, right? If I drew it a little better. So what is the big R in this case, and what is the little r? We'll look at the axis you revolved around. The little r is just from that axis through the hollow until you hit the solid, and the big R is all the way to the outer edge. So when we're going up, it's a lot easier to see that this is the little r, and the big R is changing. The big R starts as small as that, and it gets as big, right? It gets as big as this. So it looks like the little r is constant throughout this entire solid, but the big R is the one that is changing, right? And we are going to use this the slices again. So like this is the big R slice. How can we represent big R? Well, it's just the displacement between this function 4 minus x squared over 4 and 0, right? So big R is the displacement of 4 minus 1/4 x squared minus 0. Little r is a constant 2, right? This is 2, and it stays constant throughout the entire shape. So we could say that this volume is pi times the integral. First of all, this is a dx slice, right? It's a little width among x instead of y like the last videos with disk method, which means we want a function of x here. Good, we already have that, so we don't have to rearrange anything. But that means we also want x values there. So before I drew all over the shape, we were going from -3 until 3, starting at this -3 and ending at 3. That is where those slices are variable to move. They start here and they go all the way through the whole shape, right? And what is our big R squared? 4 minus 1/4 x squared minus little r squared. All right, so you see we're just kind of finding the volume of this big sphere looking thing and then subtracting off the volume of that cylinder. Remember, this part right here is just a little cylinder, and this is like the whole sphere thing. So then we have, let's see, volume. This is also a symmetrical shape, so what we can do is put a 2 out front and instead integrate from 0 to 3. It is the same volume this way as it is that way. So let's only do half the integral, but double it, and that'll make it an easier integral. Okay, so let's look at what is this all FOILed out. Well, we have a 4, and then we have a minus x squared. If you do this times this, and then when you do it again for the outer, you're going to get another one. And last, you have a 1/16 x squared squared, and x squared squared makes a x to the 4. And finally, this right here will produce a negative 4. So it looks like that positive 4 and negative 4 cancel at least. And it looks like we have 2 pi integral 0 to 3 of 1/16 x to the 4 minus 2x squared dx. So this isn't that bad of an integral, it's just 2 pi. When you integrate to x to the 4, you're going to get x to the 5th. And we're going to divide by that 5 as well. So instead of a 16, it's a 16 times 5, or an 80. And when you integrate x squared, you're going to get x cubed, divide by that new number, and evaluate at 3 and 0. So volume is just 2 pi 3 to the 5th power is 243 80ths. 3 to the 3rd power, but we're dividing by 3, so it's really 3 to the 2nd power. It's kind of like that. And finally, we could put these over a common denominator by, oh, but you know what we messed up here is that when we square this 4 right here, we should have a 16. So this right here, instead of being a 4, should have been a 16, which means that 16 minus 4 would have netted us another 12 inside the integral. So there's also a 12x from 3 to 0. So it doesn't change much except having a 36 in here now. That's good, because now the volume is positive. Figured it might have been wrong since it was negative. But let's see. Now we have 18 and 36 make a positive 18. And 18 is the same thing as 1440 over 80. Finally, we could cancel the 80 and the 2 to make a 243 plus 1440 over 40. And a little bit of simplification. Looks like we get to 1683 over 40 times pi. So that is the volume of this solid. Okay, then we move on to do the same thing with this shape. So this shape, when we revolve it, let's see, we're going to have something that looks like that from the x squared, and something that looks like that from the x to the 5th. And then this part's going to come down, and there's also going to be one on the other side. So it's kind of like a, I don't even know. It's kind of like a cone, a curved cone, but it's another curved cone cut out inside. It's a weird shape. But we can see that when we revolve this shape, it kind of makes a a disc, right? But then there's this little part, this hole cut out of it, like a washer. So we could see that this is the little radius, and this is the big radius, and both of them are changing now. So volume is equal to pi integral, where the slice is moving from and to. Looks like because of this right here, we're just going from 0 to 1. What is big R? It looks like big R is just the displacement between the top function and the x-axis, right? So big R is that, or even that. The top function is x squared minus 0, so it's just x squared. Little r looks like the displacement between the lower function x to the 5th and 0, so just x to the 5th. Co-volume pi integral 0 to 1, or let's just evaluate the integral. 1/5 x to the 5th minus 1/11th x to the 11, evaluated at 1 and 0, so volume is equal to pi 1/5 minus 1/11th. And let's get a common denominator. Let's do 11 over 55 minus 5 over 55. So finally, volume equals 6 pi over 11. That was the final answer. Okay, so these aren't too bad. It's just like a disk method, but then you have another r squared in there. But what if we don't revolve around either axis? What if we revolve around another x equals 2? Well, what shape is it going to make? We can reflect it to the other side and then connect the points. I see a cylinder. It almost looks like a little volcano, right? And we can see the little radius is a constant because it's a cylinder, and the big radius is changing. It's either as small as this or as big as that, right? So let's see, the big radius looks like just the displacement between x equals 2 and this function, x cubed. So it's this, all of those slices start at 2 and end at x cubed. How about little r? All of them start at 2 and end at 1. It's a constant. This is the value x equals 1. So it has a constant radius. This right here is a displacement of 1, so that's what little r is. Right, so now that we know big R and little r, we can say volume is pi times the integral. Where are these slices moving from and to? Well, they are moving from 0 up until this this value right here. Looks like I forgot to write it down, but it's 1. So the slices are moving from 0 to 1, and you can see that since we have horizontal slices, they have a dy, which means we need to be both our big R and little r to be functions of y, right? But it looks like we have them solved for x. So instead of x cubed, if y equals x cubed, x equals the cube root of y, or not cube root of 3, cube root of y. It's the same thing as y to the 1/3. So we could rewrite this as 2 minus y to the 1/3 to make sure that it is a function of y. So big R is 2 minus y to the 1/3 squared minus little r, which is a constant 1 squared dy, right? So volume equals pi. Let's factor that. Foil this out. 0 to 1. Square the 2 and you get 4. When you do an inner, you're going to get a 2y to the 1/3. Outer, you get the same thing. And last, you're going to get a y to the 2/3. Then we have that minus 1. And we have a dy. So let's clean it up a little bit. We have a pi, a 0 to 1, a 3, a minus 4y to the 2/3, nope, 1/3, and a 1y to the 2/3. So now let's do the integration. Integrate 3 with respect to y, you get 3y. Add 1 to the exponent, divide by that new number. So we're going to be multiplying a 3/4 in front, and the 4's will cancel. Then with this one, add 1 to the exponent, divide by that new number. Evaluate at 1 and 0. So volume is equal to pi 3 minus 3 plus 3/5. 3 and the 3 cancel. It's like we just get 3/5 pi. So it wasn't as bad as it looked. That is how you find the volume of this volcano-looking shape. Okay, then we have, last one, finding the volume of this. This one's going to be a bit tricky because we have two different kind of washers. One where this is the little radius, right, going from this function to there. One where the little radius is from this function to there. So two different radiuses means two different integrals. So let's figure out first, and we have to know where those integrals stop and start. So we need to know what y value this is. Well, we know what y value it is. It's 2. They told us. So, but what if they didn't tell us? What if they never gave us that hint there, that was y equals 2? How would you figure out the coordinates of that point? Well, how about we figure out the x value? That's a bit easier. We can find the x value by setting them equal to each other. Minus x squared plus 6 equal to x, which is the same thing as x squared plus x minus 6. Factor it to get x plus 3 and x minus 2, which means they equal each other at these two values, x equals -3 and x equals 2. Obviously, we're at positive 2, but we don't want the x value, we want the y value since we have dy slices. So plug that into either function. Remember, they equal each other at this point, so plug it into either function to figure out what the x or the y value is. This one's obviously easier. Plug in 2 in there for x and you'll get y equals 2. So we know one integral is going from 0 to 2 to cover this, and one integral is going from 2 to 6 to cover this. So let's do the integral from 0 to 2. What is the big R and what is the little r? Well, it would probably be smart to draw the shape first. Let's see, if we drew it, it looks something like this. Something like this. And then connecting all the points. That goes to there, that goes to there, that goes to there, and goes to there. Something like this, right? It's this is all hollow in the middle here. That's all hollow. So now we have a solid. But remember, we're partitioning it right here at y equals 2 to do two different integrals. So let's see, what is the little r and what is the big R? The little r, because if we were to draw some washer thing right here, right? This part is missing, it's hollow right there. So what is that radius, right? Well, it looks like it's starting here at 4 and ending at the function. The little r is not constant. So r starts at 4 and it ends at our function, which is the function there is y equals x, right? And we want it in terms of y. So we're just going to call that x. We want it in terms of y because we have dy slices. Okay, furthermore, we need big R. Looks like big R is constant throughout the entire thing. This displacement right here is big R. Big R does not change. It looks like it is a constant 4, right? It's 4 minus 0. Okay, so we're going from big R squared, 16, minus little r squared, 4 minus, since we have dy's, we want a function of y, not x. I don't know why I put x. So 4 minus y squared dy, right? That one's easy. Now let's find the volume of the other half of this shape, going from here to here. It's going to be 2 to 6. What's big R? It's still that constant 16, but the little r changes. Now the little r comes from here to that function there, right? So, what is it? Well, little r2. It starts at 4 and it ends at the function, but we want that function to be a function of y. So let's solve this for x. It's going to be y minus 6, and then negative, and then we're going to square root that. So that just means it's a square root of 6 minus y. So there's obviously some domain issues there. Y can't be bigger than 6. Good thing we stopped it there at 6 then. Okay, then 4 minus, that is now our radius function, because the radius function stops here, but this is that function. So it's going to be 4 minus 6 minus y. Okay, that's the little r. The big R is still 4. So it's big R squared is 16 minus little r squared, 4 minus square root of 6 minus y squared dy. And let's see what we can get. This one is going to turn into pi 0 to 2. We have a 16 and a minus. This will turn to a 16 minus 4y and minus 4y, making minus 8y. Finally, we have a positive y squared. There's a dy. And that is going to turn into pi. The 16 and the 16 cancel. And before we do the integration, let's clean it up. We're still going from 0 to 2. We have a positive 8y now and a negative y squared. So that one's not too bad. This one is pi. We're going from 2 to 6. We have a 16 minus 16 minus 8 square roots of 6 minus y plus 6 minus y when you get rid of the square. dy. So we were able to get rid of those 16s and these 16s. Let's see, I'm going to call this one V1 and V2 and bring them down here. So V1, we said, was this right here. Pi. When you integrate 8y with respect to dy, you're going to get 8/3 y cubed. When you integrate, wait, no, not 8/3 y cubed. When you integrate 8y, you're going to get 4y squared. And when you integrate y squared, you're going to get 1/3 y cubed. Evaluating that at 2 and 0, v2 is equal to, let's see, we still have pi. We still have the integral from 2 to 6. Let's see what we have. We have a positive 8 square root of 6 minus y. And we have a negative 6 and a positive y. So this one up top turns to pi times 16 minus 8/3 when you plug in the 2's. So it's pi. 16 is the same thing as 48/3. So 48 minus 8 leaves 40/3. So we have 40 pi over 3. Now this one's going to be a bit trickier. We're going to have to do a u sub for this one. If we call u equal to 6 minus y, du equals, well, let me split it into 3 integrals first. This is the same thing as pi integral from 2 to 6 of square root of 6 minus y plus the integral from 2 to 6 of negative 6 plus the integral from 2 to 6 of y. All of these have dy's, and I'll probably join it all back together before I plug in the 6 and the 2. But for this integral right here, we can do a u sub for the inside composite function. Du will be negative dy, which means we need a negative in there with a dy. So we'll put one out front to account for it. Now we have pi times negative 8 integral of u to the negative 1/2. I'll pull this one to the side. Du, which equals negative 8 pi. When you add 1 to the exponent and divide by that new number, you just get a 2 out front. Finally, you can plug back in your function of y for u, which was 6 minus y. 6 minus y to the 1/2 power. Okay, so let's clean it up. We have the pi. We said that that integral was going to turn into negative 16. 6 minus y to the 1/2. Then we had this integral right here. When you integrate negative 6, you get negative 6y. Finally, we have this integral, which would leave us with a positive 1/2 y squared, evaluating that between 6 and 2. Okay, so we have pi, negative 16, 0, minus 36, plus 18, minus negative 16. 6 minus 2 is 4. 4 to the 1/2 power is 2. Minus 12 and plus 2. Okay, so what does all this turn to? Well, this is 0. We have pi, a negative 36, and an 18, making negative 18. And then we have a positive 32, a negative becomes the positive 12, and a negative 2. That becomes 44 minus 2 is 42, minus 18. 42 minus 18 is 24. So all of that becomes 42 minus 18 is 24. So all of that becomes 24 pi. And of course, v equals v1 plus v2. So it's going to be 40 pi over 3 plus 24 pi. So finally, v is equal to, let's see, what is 24 times 3? 24 times 3 is 72. So we have 40 pi over 3 plus 72 pi over 3. That's equal to 112 pi over 3. And that is our final answer for the volume of this solid. So that one was a pretty tough one. Probably don't expect like that one on your test. But we do have an easier way to solve this integral using something called the shell method, which we will look at in the next video. But the washer method is pretty useful. And I actually just realized a mistake that I made right before I ended the video. This should have been integrating a positive 1/2, because right here we have a positive 1/2, not a negative 1/2. So the only thing that changes is just a few things. This changes to a 3/2, so we're instead multiplying by 2/3. So instead of negative 16, it's negative 16/3, and then of course we have a 3/2 here. So that just means this changes to a 3/2, that changes to a 1/3, and finally here, this is the only thing right here that changes. We have a negative 16/3, or let's see, that's going to stay the negative 18, but it's this right here that's going to change, because it's not a negative 16, it's a negative 16/3, and it's not a 2. We originally had 4 and a square root in there to get to 2, but now it's 4 to the 3/2 power. 4 to the 3/2 power is actually 8. So we have to just plug this into a calculator, and instead of 24 pi, I just plugged it into the calculator. Well, let's see what I would get. Instead of this 32 right here, it should have been a positive 16 times 8 divided by 3. 16 times 8 is 128 divided by 3. So instead of a 32, that should have been a 128 thirds, and that would affect the answer. It would be 128 divided by 3 plus 12 minus 18 minus 2. It would instead be 104 thirds pi. So instead of a 72 here, it would be 104 thirds pi, and 40 and 104 make 144 thirds pi. 144 times pi divided by 3. So this is the correct answer. Sorry about that, but yeah, that one is a really tough integral, and we probably could have, like, this is the main part of this section, is finding these two volumes. Then we can use the integration capabilities of our graphing calculators to skip all of this work. I just figured I'd show it for some of the people that wanted to see it, but that is how you do the washer method correctly.